Okay, picture this. That perfect profile cut is running, the machine is just purring, and everything sounds exactly right.
You're just watching the clock waiting for it to finish.
Exactly. And then, out of nowhere, it all goes wrong. You see it starting, this this messy, tangled ball of twisted metal.
The bird's nest.
It's like a nightmare wad of steel wool, and it just instantly wraps itself around your tool. The whole machine starts to vibrate, the noise spikes, and, you just know that mess means a ruined part.
Or a broken tool insert, which, can cost a fortune. And production just grinds to a halt while someone has to go in there and clear that jam.
Which is dangerous in itself.
And that visual, that sudden catastrophe, is exactly what we're diving into today. The key thing to understand, though, is that this isn't random. It's not just bad luck.
It's predictable.
Completely. It's a predictable failure that comes from a very specific, unfavorable interaction between your tool, your cutting parameters, and, of course, the material you're working with.
So our mission today is really to cut through that complexity. We want to give you the actionable knowledge to stop this from ever happening. We're not talking about cleaning up messes.
No, not at all. We're talking about setting up your process so the mess never even forms. Based on the sources we've looked at, the whole end game is to force the chip to break. Period.
Okay, so if you're dealing with these long, stringy chips, where do you start?
You immediately look at three things. First, your tool. Does it have aggressive chip breakers? Second, your feed rate. You probably need to increase it to make a thicker chip. And third, high-pressure coolant right at the cut.
And all three of those are designed to just force a fracture.
Precisely. They overcome the material's natural tendency to just flow.
Mm-hmm.
But we need to dig into why that flow happens in the first place.
All right, let's unpack that. What is the core failure here when a chip starts wrapping?
It's really a failure of evacuation. The chips are just too long and stringy to get out of the cutting zone cleanly. I mean, the whole philosophy of efficient machining is about making chips that curl up, break into small pieces, and get flushed away.
When that cycle breaks down.
That's when you get the bird's nest. The ribbons pile up, they snag, and it's almost never just one single thing. It's usually a perfect storm of a few smaller issues.
And I'm guessing the most direct culprit, the one we can control most easily, is the tool itself.
It is. We talk a lot about rake angles and clearance, but for breaking a stringy chip, the source material just hammers on the absolute non-negotiable importance of the chip breaker.
Okay, for anyone listening who isn't 100% clear on the term, what exactly is a chip breaker? It's not the cutting edge itself, right?
No, that's a great question. Think of it as a little engineered bump or a groove right behind the cutting edge on the tool's face. As the chip flows up the tool, that feature acts like a tiny wall.
An obstacle.
An obstacle, exactly. If a tool doesn't have one, or has the wrong one for the material, it just can't redirect that chip sharply enough to create the stress it needs to fracture. The chip just peels off forever like a ribbon on a gift.
That makes so much sense. So it's like an intentional flaw designed to force a break. But, okay, moving on from the tool, the second big factor you mentioned is cutting parameters. And this one seems a bit counterintuitive.
It is.
Because when you see a problem, your gut tells you to back off, right? Be less aggressive.
Absolutely. And that almost always backfires. Operators slow the feed rate down, take shallower cuts, thinking, they're being gentler on the tool.
But that's the mistake.
That's the mistake. The second culprit is creating a chip that's too thin. A low feed rate or a shallow depth of cut produces this weak, flimsy, ribbon-like chip.
And why is a thin chip so bad here?
It just doesn't have the mass or the rigidity to break itself. Imagine trying to snap a thin piece of paper versus a thick pencil. The paper just flexes, right? It bends around any obstacle.
So you want a thick, rigid chip.
Yes. That rigidity is what allows it to build up stress really fast when it hits the chip breaker and then snap cleanly. The takeaway is, if your chips are stringy, you often need to get more aggressive, not less.
Which leads us to the third piece of the puzzle, which you said is often the tiebreaker, coolant.
Insufficient coolant. We all know it reduces heat, but its other job is just as critical for this problem.
Which is physical evacuation.
It's about blasting those chips away.
Yeah.
If your pressure's too low, or, and this is a common one, if the nozzle is just aimed badly, sort of showering the general area.
Instead of hitting the actual point of contact.
Exactly. Then the coolant stream has no kinetic energy. It's not pushing anything. It's like a traffic jam. If you don't have enough force to push the cars, or in this case the metal ribbons, out of the way, they just pile up.
Okay, so those are the big three culprits. But this whole situation gets way worse when you're working with certain types of materials, doesn't it?
Oh, it's a completely different ballgame. You're talking about the challenge of ductile materials.
Right. Things like aluminum alloys, copper, some stainless steels. They are famous for creating these awful stringy chips. And you should care about this because they just behave differently at a fundamental level.
The material science here is really fascinating. When we say material is ductile, we mean it can stretch and deform a huge amount before it actually fractures.
Like taffy.
Exactly like taffy. Brittle material, like glass, shatters with almost no deformation. But with a ductile metal, when the cutting edge pushes into it, it doesn't shear off cleanly. It gets peeled away in one long, continuous ribbon.
So that ribbon we see is the metal basically flowing in a plastic stretched state, which is where those mistakes we just talked about get so much worse.
Magnified, yeah. A low feed rate on aluminum is a disaster because that chip has zero chance of breaking. But the real game changer for ductile metals is the tool geometry. You just can't use a generic insert meant for hard steel on something soft like 6061 aluminum and expect it to work.
Why is that high positive rake angle so critical here?
Because you're trying to slice the material, not plow through it. Ductile metals need a really sharp tool with a high positive rake angle. That geometry reduces the cutting forces, but more importantly, it minimizes how much the material gets compressed and deformed before it's cut.
So it encourages a clean curl.
A clean curl right toward the chip breaker.
Yeah.
If you use a lower or negative rake, you're just pushing and mashing the soft material, which guarantees it's going to flow forever.
And all that pushing and mashing builds up heat, which you mentioned is a huge problem with these materials. They get sticky.
They get very sticky. It's a phenomenon called built-up edge, where tiny particles of the material actually weld themselves to the tool face. That stickiness stops the chip from flowing smoothly, which stops it from breaking.
Which is why a good cutting fluid is so critical for aluminum.
It's non-negotiable. And not just for cooling. It's there to reduce that friction, to stop the adhesion, so the chip can actually slide off the face and hit the breaker like it's supposed to.
Okay, so we've got the root causes. But let's talk about the consequences. I've seen operators treat a small bird's nest like it's just a minor annoyance they'll get to later. What's the real damage here?
That is probably the most dangerous misconception in a machine shop. A chip nest isn't an inconvenience. It's a domino effect that costs you serious money and time. The source material had a perfect anecdote about this.
I remember this one.
A tiny nest, barely noticeable, got caught between the finishing tool and the part. It dragged across the surface, left a deep scratch, and immediately scrapped a part that had, 3 hours of machine time in it.
It's not just the material cost, it's the lost time, the lost capacity on that expensive machine.
And the first domino that falls is your machining accuracy. That tangled mass creates completely unstable, unpredictable cutting forces.
Which means vibration, chatter.
Right, and chatter means a rough surface finish, which can fail inspection on its own, and more importantly, parts that are just flat out of tolerance. Your program can be perfect, but if you've got a wad of chips interfering with the cut, the geometry is shot.
And then there's the damage to the machine and the tool itself.
Absolutely. The tool wear accelerates like crazy. The wrapped chips trap all that heat and friction right at the cutting edge, so the coating just burns off. The unpredictable forces can easily chip or break an insert.
And the load on the machine.
It skyrockets. A big ball of chips puts a huge strain on the spindle motor, on the bearings. You're risking premature machine failure down the road, all because of a few sticky ribbons of aluminum.
And we have to end this section on the most serious point, the safety hazard.
We have to. We're talking about a spinning nest of razor-sharp metal. If that thing breaks free, it can be ejected at an incredible speed. And even if it's contained, operators get hurt trying to clear that tangled nest by hand. The risk just isn't worth it.
Okay, so that brings us to the practical checklist. We need a reliable, step-by-step strategy to make sure this doesn't happen in the first place.
Let's frame it as a proactive strategy. You have to start in the hardware.
Step 1, optimize your tool design. And you're saying this has to be specific to the material.
You have to be diligent about it. Match the tool's geometry, the coating, and especially the chip breaker to the material you're cutting. For those ductile metals, you must insist on tools with a high positive rake and a razor-sharp edge. A general-purpose insert is just asking for trouble.
You need a scalpel, not a butter knife.
Perfect analogy. Step 2 is adjusting those cutting parameters. This is where you have to fight that instinct to be timid. You need to increase the feed rate.
Because a thicker chip is a more brittle chip?
Exactly. But if that's not enough, or if you can't increase the feed because of a surface finish requirement, you can use programming tricks to mechanically break the chip.
The source mentioned PEC cycles. Can you explain what that is and why it works?
Sure. A PEC cycle, in this context, just means you program the tool to pull back for a split second during a long cut, maybe just a millimeter, and then immediately re-engage.
Ah, so that little interruption is as if to snap the ribbon.
It snaps the ribbon. It breaks that continuous plastic flow. You can also program tiny variations in the feed rate during a pass. That little disruption is often enough to do the trick.
That's a clever trick. Okay, step 3. Powerful coolant delivery.
This is critical. If you have it, you must use high pressure through spindle coolant. We're talking pressures well above 500 psi, maybe even 1,000 psi for deep pockets.
And that's because the force is doing two things, right?
It's lubricating the exact point of the cut, and it's providing the sheer physical force to blast the chip away the second it's formed.
What if you only have standard flood coolant?
Then operator diligence is everything. You have to get in there and position those nozzles perfectly. You need a powerful, focused stream aimed directly where the chip is being made. Otherwise, you get cooling, but zero evacuation force.
And finally, step 4 is about the basic operating procedures that often get forgotten.
These are the low-tech things that prevent high-tech disasters. First, monitor your tool wear. A dull tool needs more force, it generates more heat, and it goes right back to plowing instead of slicing. The first sign of stringy chips should make you ask, is this insert worn out?
And the final piece is just keeping the machine clean.
Keep that chip evacuation system, the conveyor, the washdown, keep it all clean and working. If you let chips build up inside the machine, they'll just get recirculated and find their way back into the cut, causing all kinds of secondary problems.
So if we pulled this all together, it sounds like solving chip wrapping comes down to focusing on 3 areas at once. The right tool with the right chip breaker, aggressive parameters like a higher feed rate, and powerful targeted coolant.
It's a holistic problem. Every part of the system has to work in concert to overcome the material's nature.
It's funny, it seems like such a high-tech problem, with complex tool geometries and programming tricks. But so much of the solution just boils down to basic discipline.
It absolutely does. And that brings me to a final thought I want to leave with our listeners. We know fixing this requires investment in good tools, in high-pressure pumps, in smart programming. But consider the cost of not doing it.
The cost of failure.
Exactly. When you add up the scrap parts, the broken tools, the hours of wasted machine time, how much of that cost could have been prevented by just sticking to a basic low-tech maintenance schedule? How many disasters could be avoided by just replacing a dull tool on time or making sure the chip conveyor is actually clean? At the end of the day, low-tech diligence is your best defense against a high-tech disaster.